I've talked about the formulas for voltage and currents in a circuit with an alternating current. Right, I would now like to look at the power of this filament lamp that is connected to an alternating voltage. How would we calculate its power? Now we know how to do it for a direct current circuit. We've seen the formula in many videos ago when I talked about a circuit that's connected to a simple battery. So let's review that formula. Let's have a look at that. Now that formula has a few forms, right? The first form is power equals to voltage times current. That's the first, if you like, the basic form. Now if we have a resistor R, in this case this is equal to R. Okay, I can also think of other forms like V squared over R or I squared R. Okay, so for example, let me write down this form as well. V squared over R times sine, just V squared over R. But in this case, V is changing. V keeps changing. So it means that the power would keep changing as well. So let's put in the formula for the power, for the voltage, and see what it looks like. If I use this formula, then V is just this, and V squared would be the square of this. So let me substitute this into the V. I should get V naught squared over R is equal to not equal to yet, but there is the sine function bit, sine squared omega t. So that's the sine function from there. Okay, so this means that as time passes, P would go up and down with this function. But now, if I want to think about sketching a graph of P, what would it look like? So let's take a look. Okay. Now a sine squared function. Well, you know what a sine function looks like? It looks like this. It goes up and down. Okay. But this time we have a sine squared, which means that I won't get negative numbers. like for example, this part of the voltage graph, in this part of the graph, the voltage has a negative value, which means that it's going in the opposite direction. But if I square that, it won't be negative anymore, it would just be positive. Okay, so if I plot the power graph, well, the part where the voltage is 0 is still 0, right? But if V is 0, V squared is still 0. So the parts where V is 0 should also give 0 power. So there's this point, this point, this point, and so on. So I can actually mark those points out. These are the points where the voltage and power are 0. Okay. And the part where the voltage is highest, because power is related to V squared, R is fixed. So if V is highest, P is also highest. So that's the highest at that point and at that point. Now, the negative part will become positive when you square it. So this is the most negative part. When you square it, it would become the most positive. So that also becomes a maximum. So we can fill in the gap in between by drawing roughly a curve to join these points. So therefore, this is what we would expect the power time graph to look like. There's no negative parts anymore. It will all be up and it will go up and down like this. So it's 0 and then reach a peak and then come back to 0 and then go to a peak again, up, down, up, down. And okay, just to put in some numbers. Previously, I've calculated that if I assume a frequency of 50 Hertz, I take it that the frequency is 50 Hertz, then I've calculated that the period T is 0.02 second. Okay, so that would be 0.02 second, for example. And then the peak of this voltage, we can find from here, V0 squared over R. So if I call this P0, P0 would be just this part here. Okay, that's my P0. And I know that V0 is 1.5. I know that R is 10. Okay, so I can calculate that. Let me do it. So P0 is V0 squared over R. And in this example then, V0 is 1.5 and R is 10. I use my calculator, should find 0.225 watts. So that's the maximum power, 0.225 in watts. So that's what the power time graph would look like.